Well, greetings. There seems to have been a shift in the space-time continuum because today is April 19th, 2023, and I speak to you from the hallowed halls of Amherst Central High School. This is worksheet 6, and for my folks that are on their way to perform at Carnegie Hall, break some legs. But here are the solutions to the interior questions from that worksheet. Here's our set with the following data. For questions 4 through 10, refer to the reaction taking place at 50 degrees Celsius. A plus 2B plus 3C goes to 2Y plus Z. So you've got 3 reactants, you've got 2 products. Your initial rate law will take the form rate equals, please don't forget K, times A to some order, times B to some order, times C to some order. Let's look for a series of experiments where we change one thing and one thing only. I look here between experiments 1 and 2. A is not changing. C is not changing. In fact, moving this way, that increases between 1 and 2 by a factor of 1.5. And the rate also increases by a factor of 1.5. So changing B seems to have a matching effect. B is a first order scenario. I look for a second set of reactions, experiments where only one factor changes, and I find here between experiments 3 and 4, A is not a factor, B is not a factor, but in fact I have doubled C, and my rate has also doubled. C then is again first order. And now, if you look for a series of experiments where you change A and only A, you will not find it. So I'm going to take a look. Let me see if I can get this paper up here. We're going to look at experiments 1 and 3, I'm sorry. Look at experiments 1 and 3, and let's list out what we've got going on here. We're changing A, we're changing B potentially, we're changing C potentially, and they were measuring the rate of Y. Let's see what happened. Let's list out what happens here between experiments 1 and 3. A doubles. B is not a factor. C doubles. And my rate increases by a factor of 8. I also know that C is first order, which means that my rate, if I had only changed C, my rate should have increased by a factor of 2. But it did increase by a factor of 8. Take that ratio, that equals 4. That is the effect of what you did to A. Well, you doubled A, and the rate is 4 times faster than it should be. Seems to me that 4 is 2 squared. A is second order. So your rate is K A squared BC, which is indeed choice D. All right, so in number 5, we're looking for the formation of Z in experiment 3. Experiment 3, they gave me Y, so you've got 80 for Y. It's just a stoic question. Y goes down here, Z goes up there. Z is a 1, Y is a 2. Try to stay on screen here for you. 80 divided by 2, that's 40. Rate of disappearance of C in experiment 2. Go to experiment 2. You've got 15 for Y. Another stoic question. Put Y down here. They're asking us about C. Stoic says 3 C's for 2 Y's. 15 times 3 is 45. Divided by 2 is indeed 22.5. Doubling B. Well, B was first order. So, if B goes times 2, Y is what you measured, should also go times 2. That's what a first order thing does. Solve it for the rate law constant. So I'm going to take the data from experiment 1. You could choose any of them. So rate is equal to K A squared B C. In experiment 1, the rate is 10. right? So we're going to solve this for k. So 10 is equal to k times, grab your data, a is 0.1 squared, b is 0.02, and c is 0.04. So divide out by 0.1 squared and 0.02 and 0.04 on both sides. Those will all cancel, and you get k. If you're not in scientific notation, it looks very, very large, but you toggle over to scientific notation, you're going to get 1.25 times 10 to the 6th. And then finally, it says the missing rate in experiment 5, this one right here. Well, now you know the expression. You could say the rate is equal to 1.25 times 10 to the 6th times a squared bc. So 1.25 times 10 to the 6th times, go grab your data, 0.05 squared times 0.01 times 0.06, and you'll find that this rate is about 1.875, ignoring sig figs, but that is none of these. And I don't know who wrote that question, but clearly they were not loved as a child. All right, let's move on to page 2. Number 10, limiting excess. Oh dear God, those hateful words. Well, it's not that hard to figure out, but consider this for a second. In experiment 3, you've got 0.2 molar for A, 0.02 for B, that's literally 10 times smaller, and 0.08. I'm going to guess that that is what I'm going to run out of because it's the smallest number. Let's see if that's indeed the case. I'm going to rewrite my reaction here. A plus 2B plus 3C goes to 2y plus z. And let's substitute in our data from experiment 3. I had a little icebox here. I had 0.20 for A. I had 0.02 for B. I had 0.08 for C. And of course I start with no products. Now, I am guessing that the smallest value is the one I'm going to run out of. If that's true, I should be left over with excess for both of these. So let's use up all of B. That would leave me with none. If that's true, if I use 0.02B, according to my stoichiometry, B down here, A up here, 1A, 2Bs, yeah, that's going to be 0.01 for A. That looks good because that's going to leave a whopping 0.19 left behind. And if I have 0.02 for B, and I go through my stoichiometry and put B down here and C up here, that's 3 C's for 2 B's. 0.02 divided by 2 times 3, that turns it to be 0.03 C. And that's good because you've got 0.05 left over. So this is excess, this is excess, this is indeed my limiting reactant, which means I can go to the actual question. I'm going to use up all of my limiting reactant. You've got 0.02 for B, and they're actually asking you about Z. So now it's just a stoic question. B there, Z there, 1Z, 2 B's. 0.02 divided by 2, that's 0.01 for Z. Okay, next set, final set. Hopefully get through this video without too much more time. Here I have a one reactant situation, so my general form for the rate law is rate equals K times NOCl to some power. Moving this way, looks like I've doubled my concentration. So take the big number, divide it by the small number, plug in 1.44 second EE negative 8 divided by 3.6 second EE negative 9, and lo and behold, you're going to get 4. So this was times 2, this is times 4, that would appear to be second order. So this 300 here, don't let that fool you. They said you're at 27 degrees Celsius. That is indeed 300 Kelvin. So they're just saying, what is the value for the rate law constant? So pick some data. I'm going to go experiment 1, rate. Well, the rate is 3.60 times 10 to the minus 9 is equal to K times 0.30 squared, divide by 0.30 on both sides, squared. And you're going to get K, and that turns out to be 4.0 times 10 to the negative 8, which is choice C. Now they ask you, what if you went to 400? Well, that's hotter. Hotter means faster. Even with the same concentrations, it's going to go faster. If you want that rate to increase, without changing the concentration, K is going to get bigger. So it's going to be bigger than it was at 300. And then finally they ask you, by what factor would the rate change if the initial concentration went from 0.3 to 0.4? Well, big number over small number, if you take 0.4 over 0.3, understanding that this is a second order function, that turns out to be 1.7 repeating run-on, which is about 1.8. All right, I hope this helps. Enjoy the ride. Have a great time in New York City. See you when you get back. Adios.